I hope tonight finds everybody well. Hope you've had a great day and are ready to do some logic. Today, we're going to talk about symbology and truth tables. So you're going to learn about these new symbols, you're going to learn how to translate them, and then we're going to learn about truth tables. Okay. So I want you to just take a minute, just review what we've done, and I want you to take the two statements. You take geometry, and then you take French, and I want you to write the conditional, the converse, the inverse, and the contrapositive. Pause the video, and when you're ready to check, go ahead and play. Okay, so we have for the conditional, if you take geometry, then you take French. For the converse, if you take French, then you take geometry. The inverse, if you don't take geometry, then you don't take French. The contrapositive, if you don't take French, then you don't take geometry. And the biconditional is not possible because both the converse and the conditional are not true. Okay? Because if you take geometry, you don't necessarily take French. Okay. So, moving on. We had these symbols we've talked about already. The first is it implies. We use it in an if-then statement. The second, either the tilde or that little bar, that bar has to be facing that way, negates a statement. The three little dots is therefore. And then the arrow going both ways is a biconditional, or an if and only if statement. All right, so just a quick little review. We're going to add some symbols. We're going to add this upside down V, or this caret, and that's going to be an and. In an and statement, for the whole statement to be true, both parts must be true. And I want you to think back to algebra when we did compound inequalities. For a compound inequality, say y, or whatever, x is greater than or equal to -3, and y is less than or equal to 0. Both of those things had to be true, and we kind of did them on the number line so you could get a nice little visual. So we do -3 and 0. These are the compounds where they come together. So closed circle, and your solution set is in between. Okay, so those come together. Both things have to be true. This upside down V is an or statement. And in an or statement, at least one part has to be true. Both could be true, but at least one part has to be true. And if you think back to algebra, and again in those compound inequalities, something like x is greater than 4 or x is less than 2. Okay, so these were the compound inequalities where the arrows went in the opposite direction, and there was actually, in the algebra's case, in the compound inequalities case, there's absolutely no way both of those things could be true. Here, both could be true. But think back to that, just relating it back to Algebra 1 and something that you guys know since you miss algebra so much. Okay, so now let's look at some of these statements. P, if you build it, in the Q, they will come. So the P with the arrow, double arrow in between it, is the biconditional. You will build it if and only if they will come. Okay. We have our new symbol. This is an or. Yes, an or. I remember them because the and looks like an A, except without the little bar. I have little tricks. Okay. You build it or they will come. So let's just assign truth values to these just so that I can show you. So let's assign a true to this and a false to this. That's F. So you will build it or they will come. This whole statement, because it's an or, this part is true, this part is false, and our statement then would be true because it's an or, and only one part has to be true. Okay. If I were to write it in and, you will build it and you will come. It should be and they will come. Okay. This is a true part. This is a false part. So the whole statement is going to be false. All right. Notice that in these and or statements, we didn't use if and then. We just straight out said, you will build it or they will come. You will build it and they will come. Okay, so let's look at these truth values here. I've got emperor penguins are black and white. Okay, I know that statement is true. That's my X. My Y, polar bears are endangered species, is true. At least last time I checked, people come on and off those lists, usually through different things. And penguins wear tuxedos is false, only in cartoons, right? So if I have my statement, X and Y, it means that emperor penguins are black and white, and polar bears are endangered species. So this is true, so the whole statement is true, since both parts are true. Now, if I wanted to change it and do the or statement, emperor penguins are black and white, or polar bears are endangered species, both parts are true, so it's not going to change anything. That's still going to be true. Our third statement, emperor penguins are black and white, and penguins wear tuxedos. So the premise, the emperors are black and white is true, penguins wear tuxedos is false. This is an and, so both have to be true. So that would make this a false statement. Last example, emperor penguins are black and white, or penguins wear tuxedos. So true and then false, but since it's an or, you only need one part to be true. All right. So these are just how we use these statements, and it leads us to this thing called a truth table. And a truth table lists all the possible combinations for true or more statements. So I'm just going to go through. I've got these statements. Ohio is a state. I guess so. It's true. I tend to forget about Columbus usually. There are 50 states. That's true. So my if-then statement, P then true, according to the logic that we learned earlier, this would be true. P and Q, both parts are true, so that's true. P or Q, both parts are true, so that's true. So everything's true in this example. Okay. Ohio is a state. Again, yeah, true. Miami is a state is false. Okay. So if the premise is true and the conclusion is false, we say that this is false. Okay. Then we have the and, both parts, the premise and the conclusion. So both of these have to be true. They're not. So this is false. Again, P or Q, only one of these needs to be true, and this is true. So that means that this is true as well. Okay. Now, this gets a little weird to me. 2 plus 2 is not 5, so that's false, and 2 times 2 is 4, which is true. And we think back to our logic with the if-then statement. If the premise is false and the conclusion is true, the whole statement would be true. I know it seems odd, but it is. Okay. So now, the and, P and Q, both parts have to be true for it to be true. So that would have to be true. That would have to be true. And it's not, so it's false. Okay. And P or Q, again, only one part needs to be true. And only one part is true. So that's true. All right. 2 plus 1 is 5. Not on this earth. So that's false. Dolphins are big fish. Nope, they're mammals. So thank your life science teacher for that. Okay. Now, when both of these are false, a premise is false and the conclusion is false, again, the if-then statement is true. Okay. All right, and then when I go to my and statement, neither of them are true, so this would be false, and the P or the Q, again, neither of them are true, so that would be false. So the thing with these truth tables is we can play around and we can do knots with it, we can do inverses, we can do all kinds of things. So you just have to stop and evaluate it every time you do a truth table. Okay. So what did you learn today? Today you learned that the symbols for and or, and kind of an A without a bar, or like this, we were reminded that for an and to be true, both parts have to be true. Just like we took it back to compound inequalities. And then the or, the upside down V would be or, and only one part has to be true. And then we learned to do some truth tables. So logic, again, not real mathy. I know you guys, I get your point. I like the algebra, but this is more like a language arts class. Let's just roll with it and see where it goes. Have a great night, and I'll see you at school.